So welcome everybody to this colloquium, which is organized by the Department of Mathematics and the Institute of Mathematical Research of the University of Hong Kong. We are very glad to have Professor Robert M. Strang from the University of Pennsylvania here. Professor Strang is an expert on the Boltzmann equation, and he will talk about his recent breakthrough in the relativistic case today. Let us welcome Professor Strang, and I will hand over to him right now.
Oh, hi. Thank you, Danny. Thanks very much for the invitation to speak here, and thanks everyone for coming. I'm very happy to have the opportunity to talk today to you about my research on the special relativistic Boltzmann equation from kinetic theory with the long-range interactions. This is, oh, can I? Yeah, okay, I did that. I couldn't hear. Okay, so today I'm talking about the relativistic Boltzmann equation with long-range interactions. This is a joint work with my former PhD student, Jinwoo Zhang, who's a researcher at the University of Bonn right now. And it's one of these papers, actually, the first one, is also a joint work with James Chapman, who used to be an undergraduate at my university, at the University of Pennsylvania. And he got involved in this project in that way because he was helping me with some numerical experiments. And now he's a graduate student at UCLA in mathematics. So I'm going to tell you about these three papers. They're connected, so it's not really three different results, but it's a chain of research. So what I'm talking about, you can see that is a relativistic Boltzmann equation from kinetic theory, and it's a model of gas dynamics. So here, this is the partial differential equation. So it's F is the unknown function, and it's a probability density in position and velocity, where X is position and P is velocity and T is time. And omega is some kind of a spatial domain, and this quantity P over P0 dot gradient XF is a free transport term. It represents just free transport, pushing forward with no obstructions. And P is the momentum variable. It has three components, so it's an element of R3. And in relativity, we also use the notation P mu, where P mu is a 4 vector. It has 4 components. It's P0 and P, where P is from over here. And P0 is the relativistic energy. It's the square root of 1 plus P squared, where this is the Euclidean, P squared is the Euclidean distance of the 3 vector P. And P0 is a relativistic energy. And then Q is a local in TX collision operator. And you can write as QFH and it's this integral. So we call this non-local because it's an integral over dq and d omega of these quantities v theta, which is the molar velocity, and sigma, which is a collision kernel. And then you have fp prime hq prime minus fp hq, and you're integrating this. So this is this model explains the effects of collisions in particle dynamics. So here v is the molar velocity, and it's this relativistic invariant quantity. It's kind of like the distance p minus q, but it has to be relativistic invariant. It has to be Lorentz invariant. So it becomes this quantity, which is the absolute value, the square root of the absolute value of p over p0 minus q over q0 minus the cross product of the same things, same two quantities squared. And so that's a kind of part of the kernel of this integral, which helps you measure how the amount of particles change in a small cubic centimeter, say, of a gas, due to collisions of particles. So you think we're studying particle dynamics where the particles can move close to the speed of light. And if you try to take a probability density to tell you where the particles, how many particles are in a given location, then you can derive this equation here, which is the relativistic Boltzmann equation. So I'm not going to talk a lot about the derivation. I'm going to talk about the properties of solutions. And so I'm just introducing the equation to you here. And now I can tell you a bit about the quantities in the collision operator. So you may remember in the previous slide that I told you that there are these quantities P prime and Q prime. And those are the post-collisional momentum. These are the momentum, the speed, if you will, of particles after they collide. So if you have two particles colliding with incoming velocities P and Q, then their outgoing velocities or momentum are P prime and Q prime. And P prime is P over P0, P plus Q over 2, plus G over 2, plus this complicated thing that's all defined here. But let me not read it to you completely carefully. And the angle in the kernel of the previous expression that I showed you is cosine of theta, and it's defined as 1 minus 2 g of p prime squared over g of pq squared. And this is, if you're used to sort of Euclidean geometry, it's not obvious that this is an angle, but it is known to be a well-defined angle. So cosine of theta stays between -1 and 1. And in this expression, G is called the relative momentum, and it's this quantity. It's G of PQ is 2 P0 Q0 minus P dot Q minus 1 squared. And this is actually sort of like a Lorentz invariant distance. It's kind of like P minus Q if you want, but if you want things to be Lorentz invariant. And S is this quantity G squared plus 4 that I wrote there. So this is these are some of the quantities in the collision operator. And then I'll say how we get them. So given two particles with momentum P and Q after a binary collision, they have outgoing momentum P prime and Q prime in R3. And these momentums satisfy these conservation laws here that P mu plus Q mu is equal to P prime mu plus Q prime mu for all the mu in 0, 1, 2, 3, for 0, 1, 2, 3. And this you can use this these four conservation laws to get the expressions on the previous slide for P prime and Q prime, and you can also derive formula for P prime 0 and Q prime 0 using these expressions if you get a little creative. And you get these expressions. So P prime 0 is P0 plus Q0 over 2 plus G over 2 square root of S plus times P plus Q dot omega. And Q prime is similar, except there's a minus sign there. And so this is interesting because these expressions are also defined as the square root of 1 plus P prime squared, and it's not so easy to see that that quantity is equal to this quantity, but it is. Okay, so these are some of the expressions. And now I want to give you the hypothesis on the collision kernel. And the hypothesis on the collision kernel are as follows. So sigma of G theta, which was defined in the, this is the what I call the collision kernel. It's assumed to be phi of G times sigma 0 of theta, where phi of G is non-negative, and sigma 0 of theta is also non-negative. And phi of G is can be thought of as kind of a power law, and so you can write it as a constant, which I call C phi times G of rho. And this angular function, sigma of theta, is not locally integrable. If you just integrate it, it blows up. And you can think of it as sigma 0 of theta is the order of theta to the -1 minus 2 gamma for gamma between 0 and 2. And say for theta between 0 and pi over 2, you can use that as the assumption. And our assumption for rho in sigma can be taken to be rho less than 2 and bigger than -3 over 2 minus gamma. And this makes this operator phi also singular near p equals q if rho is negative. And so here we call these collision kernels the hard potential case if rho plus gamma is greater or equal to 0, and we call this the soft potential case if rho plus gamma is less than 0. And this full set of physical assumptions for the collision kernel was proposed by two physicists, Dudziński and Ikoł-Juniska, in their joint paper in 1988 in Communication and Mathematical Physics. And this collision kernel makes the relativistic Boltzmann equation into a non-local fractional diffusion equation, which I like to tell people is something that was not necessarily understood what that was at the time when this equation was written down. So the Boltzmann equation was written down in the 1850s by Boltzmann and Maxwell, and the 1860s. And they, in this non-relativistic case for Newtonian physics, and in that, and they wrote down, they derived a collision kernel that had similar behavior to this one, using a power law potential. And it wasn't until more than 100 years later that people actually knew how to write down non-local fractional diffusion rigorously in mathematics. But here's an example of a physical equation where that behavior was exhibited long before the tools needed to study it were known in mathematics. And the physicists didn't necessarily, even Boltzmann and Maxwell didn't really know the modern language of non-local fractional diffusion equations either. Okay, so here is the hypothesis on the collision kernel, and this is what it tells you. It tells you that Boltzmann equation and the relativistic Boltzmann equation are non-local fractional diffusion equations. And so I'll give you some examples to show that this is not made up. So this really comes out. And this the first example is Mahler scattering. And so, for example, it's written in this paper by de Groot, Van Leeuwen, and Van Wert. And this is the expression that they give you. And this is very singular. This might be sort of the analog of the Rutherford cross-section in Newtonian, for the Newtonian Boltzmann equation. And this second example is these Israel particles that were derived by Israel in 1963. They were used by physicists to study properties of the relativistic Boltzmann equation. And here you have this B theta, which can be singular, which is an angular function. And there are other example kernels such as short-range interactions, Compton scattering, and a neutrino.
Improve value of the projects, challenge the status quo,
and neutrino gas is the other one. So these are the examples. For the Newtonian Boltzmann equation, you can actually derive these collision kernels from particle dynamics. Unfortunately, in the relativistic case, the issue of having a well-defined relativistic particle dynamics is still, as far as I understand, a big open problem in physics. And one issue is that the notion of having a particle at a distance, using a potential at a distance to define relativistic particle dynamics is not consistent with the laws of special relativity because it implies there's instantaneous communication. Excuse me, I'm going to drink of water. So instead, these collision kernels are derived using Feynman diagram techniques, and they're found in quantum physics textbooks, because that's, and and this is really an approximation. This is an expansion of using Feynman diagram techniques, and this is like the first 3 terms. That's how they do it. Okay, so there's also a relativistic Maxwellian equilibrium, which are called the Juttner solutions because Juttner derived them. So equilibrium states are characterized as a particle distribution which maximizes the entropy subject to constant mass, momentum, and energy. And in the full physical generality, they can be written as J at P is equal to E minus C P0 over KBT divided by 4 pi C KBT times the Bessel function here. And C is the speed of light, KB is Boltzmann's constant, T is the temperature, and K2 stands for this Bessel function that comes out if you want this to be integrable in L1. And then the Juttner solution with normalized constants is just this one. So it's J of P is E minus P0 over 4 pi. And this one has a unit L1 mass. Okay, so, and these are the equilibrium solutions to the equation, or some of them. And here's a short, incomplete list of results on the relativistic Boltzmann equation. So Leshnerowitz and Marat derived the equation using special relativity in 1940. Bichler proved local existence to the equation in 1967. Dudinsky and Ikol-Jouniska studied L2 solutions to the linearized equation in 1988-89. They also studied the theory of de Bernard's renormalized weak solutions for the equation. Then Glassie and Strauss started studying the stability problem in 1993 when they proved the unique global smooth solutions on T3 and exponential decay for the Hart potential case. And in 1995, they generalized their work to the whole space result with polynomial convergence rates for the Hart potentials. Andreasen in 1996 proved regularity in L1 stability. Weinberg in 1997 proved the regularity of the gain term type result. And then Andreasen, Calogero, and Reinhard Illner in 2004 studied the issue of blow up for the equation. If you only have the first gain term and you throw away the loss term. Yang and Yu in 2010 proved a hypocoercivity for the relativistic Boltzmann equation, and I worked on this in 2010. I studied global existence and stability for the soft potential case, and with my collaborator Jared Speck in 2011, we proved the Hilbert expansion for the relativistic Boltzmann equation between the relativistic Boltzmann equation and the relativistic Euler system. And with Kia-Zhu in 2012, I studied the soft potential case in the whole space, proving global existence stability. And in 2017, Renjen Duan and Yu proved global existence and strict exponential decay for the soft potential case in the torus. So that's a short, incomplete list of results for the relativistic Boltzmann equation. Nowadays, there's a lot of results being proved. So I could easily tell you about several more slides of results. I should say that all of these results use the so-called grad angular cutoff assumption. So the results that I'll tell you about are the first ones that study the full collision kernels that were derived from the physics that I told you about earlier. But first, let me tell you about the Newtonian Boltzmann equation. So I put this to 1872 here, but it depends on what you look at, really, but on the date that you give for the derivation of the equation. And so you have dtf plus v dot grad xf equals qff. So it's a similar equation, except we replaced p over p0 by v. So p over p is the momentum and p over p0 is the velocity. And here we're just calling v a variable and saying it's a velocity. That's one of the things that makes this Newtonian. And then v dot grad x is the free transport term, and qff is the collision operator, which is quadratic and is local in t and x. And it looks like that. So you have the integral over dv star, d sigma, you have the kernel b, and you have f of p prime star g of v prime minus f of v star g of v. And the pre-post collisional velocities v star and v prime v star prime star satisfy these expressions. So if v and v star are the velocity of two particles that will collide, then after collision, their velocities are given by these quantities, and the sigma parameterizes a sphere as written here. Okay, so as you can see, the post-collisional velocities are much simpler. And you have show you sort of a very brief list of non-cutoff results for the Newtonian Boltzmann equation. So you have this result by Pao that I mentioned from 1974. Pao was a postdoc at the Quran Institute, and he proved a very interesting result using special functions to study the non-cutoff Newtonian Boltzmann equation. Then there was kind of a long gap until more people started studying this. And in the year 2000, Alexandre de Villeneuve and Wenberg proved some results. In particular, they proved the regularity of the collision operator, and they introduced something that was called the cancellation lemma that I'll tell you more about. And Alexandre Villeneuve then in 2002 proved the existence of renormalized weak solutions with defect measure for the Newtonian Boltzmann equation without angular cutoff that generalized the results of de Broglie to the case without angular cutoff. And Yang Guo proved in 2003 the global stability of the Maxwell-Boltzmann system near Maxwellian. That was for the cutoff Boltzmann equation, but the results are very useful and important for what I'm talking about, so I mentioned that too. And then with Clément Mouhot, I studied the spectral gap for the non-cutoff Newtonian Boltzmann equation. And then in 2011, Alexander Morimoto, Yukai, Zhu, and Yang, and also in a different but related work with Phil Gressman, I proved, so these were two different groups. One of them was me and Gressman, another one was those five authors. We proved the global stability of the Boltzmann equation, the Newtonian Boltzmann equation, close to equilibrium, close to the Maxwellian equilibrium. And I'll say more about that later. But then in 2017, he and Zhang studied the mild-tailed global stability near equilibrium for the hard potential non-cutoff Boltzmann equation. And Harao, Tanon, and Tristani in 2017 studied the mild-tail global stability for the hard potential non-cutoff Boltzmann equation, also using work by Gualtani, Mishler, and Mouhot. And then in 2019, Jonathan Luke studied the stability of vacuum for the Landau equation with moderately soft potentials. So that's a very closely related equation, but it's not. And then his PhD student, Sharavendi, last year, wrote a paper proving the stability of vacuum for the non-cutoff Boltzmann equation with moderately soft potentials. So building on Luke's results. So that was, so these two results are near the vacuum state, which is the zero equilibrium. But they're also very interesting and related works. Okay, so that's kind of some of the history, very incomplete, but that's, if it were going to be complete, it would take a lot longer to explain it to you. Okay, so the Newtonian cancellation lemma is a very important result that came from the work of Alexander de Villeneuve and Wenberg. It wasn't really their main result in the paper, but that's why they called it a lemma, and that's why it's been called the cancellation lemma. But it turned out to be a very important result for the study of the Newtonian Boltzmann equation, because it was very useful. It's kind of like integration by parts in calculus in some sense. So everyone just takes it for granted, but it turns out to be one of the most useful things anyone can do in analysis and in partial differential equations. And in this field, the cancellation lemma played a little bit of a role like that. So your collision kernel is V of V minus V star sigma, and you can model it as V minus V star to the alpha times theta to the minus 2 minus nu for alpha greater than minus 3 and nu in 0, 2. So this theta variable is to the minus 2 minus nu is very singular, is not integrable. And then you can see that by the integral dv d sigma of b times f of b minus f of v star, the cancellation lemma says that this is equal to f convolution s in of v star, where that's just the normal convolution. And here s is a constant c3 times the modulus of z to the alpha. And this can be proven for a very general class of functions f. And this is based on the change of variables v prime to v with Jacobian determinant equal to 1/4 cosine theta over 2 squared, which for theta between 0 and pi over 2 is greater than or equal to 1/8, which is non-negative, which is strictly positive. And so this was a big part of the foundation for proving estimates of the non-local fractional diffusion for the Newtonian Boltzmann equation. And so now I can tell you a bit more about the Newtonian cancellation lemma. So in general, consider the difference. U is theta v prime plus 1 minus theta v, and theta is in 0, 1. And then the change of variable from u to v has Jacobian determinant. The u dv is 1 minus theta squared times 1 minus theta plus theta cosine theta, like that. And this for cosine theta greater than or equal to 0, this is greater than or equal to 1 minus theta over 2 cubed, which is positive, strictly positive. So the Jacobian determinant is strictly positive for all theta in 0, 1. And various versions of this change of variables have served as a foundation for proving virtually all estimates of the non-local fractional diffusion for the Newtonian Boltzmann equation. One of the products of this work that I'm telling you about is to show that in the special relativistic situation, surprisingly, the analogous change of variables is generally not well defined. And this is kind of a horrible story, but it has a happy ending. So this is the first work that I'll tell you about. So this is Chapman, Zhang, and myself. And in the relativistic case, if you let u equal theta p prime plus minus theta p, then you can actually calculate this Jacobian determinant, and it takes the form a cubed plus p2a squared plus p3a, where a is this ugly quantity. It's actually not that different from the previous quantity, but it's significantly uglier. And P2 and P3 are very horrible expressions which satisfy the following bounds that I won't make you stare at for too long, but I just want to be honest and explain all the results. And then, okay, so you can even calculate these quantities, and there they are. So you don't have to look at this long enough to understand that, but you can just see that there's some big weird expressions with a lot of different quantities in them. And so this is the Jacobian determinant of the derivative of the collision map. And in order for this to be a change of variable, we would want that determinant to be strictly positive. However, that doesn't seem to be the case. So we use numerical techniques to gain some understanding of the zeros of this Jacobian, and random sampling of the domain showed that most points gave the determinant to be positive. And so we wanted to find zeros of this determinant. And so we reduced the problem to finding values which make the determinant negative. So following this, we picked another point with positive determinant and performed the bisection method along a path between these points. So we basically kept calculating values as determinant and letting it get smaller and moving on a line until it went to 0. We were kind of wandering and finding the line as we went. And this script was written in Sage Math by James Chapman, and it was run in the general purpose cluster at the University of Pennsylvania using one node. And in order to guarantee high precision, we set the precision to 200 bits, which means it had like 200 degrees of accuracy beyond the decimal point. So it was very close to 0. And we plotted these figures, and we found a lot of zeros. So we found, we basically could find as many zeros as we wanted. There were many, many, many zeros. We had more data than we knew what to do with. And so this is just some of it. This is more of it. So these are the pictures that we found. And so there's basically zeros. This is a plot obtained by taking PQ omega is W, and when the Jacobian is 0, and expressing them in spherical coordinates and plotting the angular parts at lighter color correspondence to larger theta. And we basically found no structure to the location of the zeros. The location of the zeros appeared to be everywhere. So this was bad news. We were hoping that this wasn't true, but we found that was true. And so I could tell you more about these, but let me just move on. And then so later with Jingwu Zhang, and motivated partly by the numerical results, we figured out that the cancellation lemma in the relativistic case is actually false. So it's not just sometimes badly behaved. Here's a counterexample. So formally write down the following relativistic quantity, which is very similar to which is exactly the form of the cancellation lemma. So this is the kernel in the relativistic case, and we form J of Q minus J of Q prime, where Q prime is the variable with the prime, and I call the first quantity zeta tilde B, and I call the second quantity zeta tilde B2. And we recall that this is the relativistic Maxwellian J, it's e to the minus P0, and this is a Schwartz function. It's much better than a Schwartz function. But and so if you merely assume that the kernel sigma is constant, which is a very mild assumption, and you can prove this at any greater generality too, then it happens to be the case that zeta tilde 1 is finite, but zeta tilde 2 is infinity. And so this directly implies that there cannot be a cancellation lemma for the relativistic Boltzmann equation, because if there were a cancellation lemma, then this could not be true. And this statement is moreover independent of the coordinates that you use. So you do have some choice in the coordinates that you use in Q and Q prime, and this statement happens to be independent of those. So that's a problem, that we don't have a cancellation lemma. Excuse me, so we don't know how to prove the cancellation yet. Well, I will tell you how to do that today, but the normal way of using this change of variables doesn't work. So now, but first, before I take that, let me sort of back up a little bit. So you linearize the relativistic Boltzmann equation in the following way. So you take f equals j plus the square root of j lowercase f, and the perturbation lowercase f then evolves according to this equation, dtf plus p over p0 dot grad xf plus lf is equal to gamma of ff, and the nonlinear collision operator is gamma of fh, and it can be written like this way in terms of q, and the linearized collision operator then can be written in terms of gamma like that. And the moral to this story is that to prove global existence of nearby equilibrium, it will be essential to quantify with a sharp norm the precise behavior of the linearized collision operator. So these global stability results, using the methods that we use, is essential to characterize the sharp norm that characterizes the behavior of the linearized collision operator. And I'll tell you about that. But first, let me tell you about the further decomposition. So we have zeta tilde, which is this quantity that comes out of the linearized collision operator. And I can decompose zeta tilde as zeta plus zeta kappa. And then I can decompose the linearized collision operator as a norm part n of f plus a weakly compact part k of f. And the norm part is defined like this. It's a zeta of p times f of p times this norm piece. And then the weakly compact part is defined like this. And then so we have this sort of essential frequency multiplier theorem. And it says, suppose that angular function sigma 0 satisfies the non-cutoff assumptions on the collision operator, then the frequency multiplier zeta tilde p can be split into the sum of two frequency multiplier functions. Zeta tilde is equal to zeta plus zeta kappa. And these multiplier functions satisfy the following sharp asymptotics. So zeta kappa is bounded above by a constant times p0 to the rho over 2 plus epsilon. And zeta is comparable to p0 to the rho plus gamma over 2. And here C epsilon is the constant that satisfies for any small epsilon. There is a finite constant C epsilon such that the above holds. And so these these are the sharp asymptotics for this frequency multiplier. And this is kind of the analog of the result of Pau from 1974 that I mentioned to you for the Newtonian-Boltzmann equation previously. But this was very hard in our case. I mean, this is probably the hardest I've ever worked in my life on a point-wise estimate. And without this result, we would not know how to prove global existence and uniqueness of solutions in our theorem nearby equilibrium. So this is essential because this characterizes the sharp behavior, and if you don't know this, then you can't characterize the sharp behavior. So I'll quickly give you an idea of the proof. So I'll throw a lot of formulas here, but I don't really want you to look at them. But I did want to write them down to kind of be honest. So I mean, I want you to look at them, but I don't want you to worry too much about understanding every detail in them. So one idea is the following. So you can do this transformation. Zeta tilde is zeta 0 plus zeta L. And I want to throw off lower order terms as frequently as I can. And so I can write zeta 0 like this, and it has this difference in it, which is essential because there's a singularity here which is not integrable. And so you have to incorporate this cancellation, and then zeta L is lower order. So we just throw it away. And this is complicated because it includes a modified Bessel function. And so you're taking a fractional derivative of a special function. And there aren't a lot of formulas for these kinds of quantities to understand their asymptotics. And then you have all these precise definitions of these formulas here. And we want the sharp asymptotics of zeta 0. But a major difficulty in obtaining the sharp asymptotics of zeta 0 is inside this integrand, which characterizes the cancellation. So here, this is 0 at y equals 0, which is what we need, and it converges to 1 as y goes to infinity, which is fine. And however, this has its negative minimum here, at this expression, ym is a negative minimum. And so this expression is negative at the minimum, and the difference above remains negative. For example, if cosine of theta is 0 until you get to here, which is another number. And so sort of in this region, the whole integral is negative. So the whole integral is negative in a large region nearby the minimum of the difference and nearby the singularity of the kernel. And so there's negative parts and positive parts, and they're mixing together. And so from this point of view, it's very, very unclear whether or not zeta 0 is positive or leading order term. And so it's very hard to quantify the pointwise behavior, and that's an essential component of proving a result like this. And so for this reason, because that expression was unclear, we derived another representation of zeta tilde. So we can alternatively derive a representation of zeta tilde like this, and you don't have to look at it too carefully, but then you can also decompose zeta tilde as zeta tilde 0 plus zeta tilde L, and zeta tilde L will be lower order, and zeta tilde will look like this, zeta tilde 0 will look like this, and this quantity in here is the difference. Some complicated expression, and there's actually two special functions in here, which I've hidden in the exponential of the cosine of theta and the extra integral here, but which make things hard. But however, and this quantity has similar problems using its maximum. So this is a better quantity in some ways, but its maximum is ym, and it only remains positive on y between y0 and ys. And so this quantity can also be positive and negative. So this quantity is actually positive near its maximum, but it becomes negative, and it's still negative in a substantial region near the leading order behavior. So it's very hard to quantify the pointwise estimates in this way. And so the magic thing that we eventually noticed was that you can, even though these two quantities themselves are bad, they're bad in different ways, and somehow if you add them together and look at them in the right way, then at the end of the day there's a square hiding, and so this term is automatically positive. And so that was kind of our very exciting feeling that we got when we figured this out. So this is a crucial insight that we use to prove the frequency multiplier theorem, that eventually you can find a square in this big mess. And then 40 pages later, after that, you can prove the theorem that I told you about, the sharp asymptotics. Okay, so now we can skip ahead. Now I'll tell you about the Boltzmann sharp linearized fractional derivative norms. And so Alexander, Morimoto, Yukai, Yu, and Zhang and the Newtonian Boltzmann equation use this norm to characterize the sharp behavior. This was called the triple norm. And it's basically part of the Dirichlet form because you use the collision operator directly. And in my work with Phil Gressman, we use this norm, and where D is, so you have a more traditional fractional derivative norm with a metric, and so this the metric here is not the flat Euclidean metric, it's the metric on the parabola. It's d of v prime is v minus v prime squared plus v squared minus v prime squared. And so this metric is a metric on the parabola, and this shows that, and this is the sharpness norm sharply characterizes the linear behavior. And so this shows that for the Newtonian Boltzmann equation, the diffusion is sort of geometric, and it's non-isotropic, and it's reflected by the geometry on the parabola. And but turns out that for the relativistic Boltzmann equation, the diffusion is actually an isotropic flat fractional derivative norm. So this is a standard fractional derivative norm. There's no metric, there's no other than the Euclidean distance, and it's normal. It's like more standard non-geometric Euclidean diffusion. So this is a flat weighted fractional derivative norm. The difficulties for the Newtonian Boltzmann equation were, I might say, in some sense, largely characterized by the geometry of the diffusion, and the difficulties in the relativistic case that we've recently resolved are different because the diffusion is flat, but there's no cancellation lemma, so there are problems establishing estimates using cancellation not related to the geometry of the diffusion. Okay, so you can define a bunch of standard Sobolev spaces let me not dwell on that, the existence of time. And then we can prove the global existence of unique solutions. So with Jimu Zhang, I proved, so fix some derivatives and put your initial data in a Sobolev space with weights. The weights are defined by the quantity L. And then there's a small constant eta such that if your initial data is small in the Sobolev norm, then there exists a unique global solution F to the relativistic Boltzmann equation, which satisfies that it's in L infinity H and L, intersect L2 and this space where you have the gain of that gamma, this flat fractional derivative space that I just introduced you to. So this is so you have a global existence of unique solutions, and they can be smooth. One thing we didn't prove is regularization, but hopefully someone can do that. It might not be me, but I think it's probably okay. It's probably a problem that's worth studying. It's not one that I have studied yet. But we also prove the long time behavior of solutions. So if your initial data is initially in H and L plus M, so you have a little bit more weights, and your H and L plus M norm is small, where for the hard interactions case, we assume M and L are greater equal to 0. And for the soft interactions case, we assume M is greater equal to 0. And L is strictly bigger than this constant. Then for some fixed lambda in the hard interactions case, we have exponential decay to equilibrium. So the perturbation decays to 0. And so this whole solution converges to the Maxwellian equilibrium. And for the soft interactions case, if you put a little bit more, this much weight on the initial data, and you have some additional weight M on the initial data, then you can get arbitrarily high polynomial decay of the solution. Okay, so so you have the convergence to equilibrium with these explicit convergence rates, and this is how we prove large time behavior. Okay, how much time do I have?
10 minutes.
Okay, good, perfect. So now I'll tell you a little bit about the proof. So we have a few different. I'll tell you a little bit about part of the proof actually. So the end of the talk is going to be about the how do you prove cancellation? How do you prove cancellation estimates for the Boltzmann equation? For the relativistic Boltzmann equation, when you don't have a cancellation lemma to estimate the fractional diffusion. And so we have a variety of tools that we've developed. So the first tool is this thing that we call the center of momentum reduction. And so for an integrable function G, which maps a lot of variables into R, we have the integral of dp prime and the integral of dq prime, and then you have the kernel, and then you have this delta 4 function. So this is actually 4 delta functions of these quantities, and there are 4 different linear equations in here. And then you have this function g, and g is a function of all the variables. Then you can reduce this to an integral over d omega of v, the molar velocity v theta times sigma times g of these variables. And to do this, you only have to assume that g has sufficient vanishing conditions so that the integrals above are well defined. This transformation enables us to do linear changes of variables if you include all the integrals in the expression. So one thing to notice here is that, well, let me say that later actually, but the point is that the second expression is like the relativistic Boltzmann collision operator, and the first expression is has more variables in it that you can integrate over. And another quantity that we derived is something we call the relativistic Colloquium representation, because the Colloquium derived different representation for the Newtonian Boltzmann equation, but the proof is similar in spirit, although not quite the same. And so if you integrate over dp, dq, dq prime, dp prime, so these are all relativistic invariant quantities. That's why you divide by p0, q0, q prime 0, and p prime 0. And you have s sigma, and then you have this same delta 4 function from before. And you have this g from before over, which is a function of all the variables. Then this can be reduced to an integral over dp over p0 dp prime over dp prime over p prime 0. And then you have this other integral over a hypersurface. And so we assume G has sufficient vanishing conditions so that the integrals are well defined. And here E is a two-dimensional hypersurface, which is defined like this. This is a Lorentzian product here. And so this is a function of Q, and it maps over Q when this quantity is 0. And similarly, you can define the measure as a dq over this quantity. So this is a different way to write the hypersurface actually. And u is a function that's 0 if x is negative, u of x is 0 if x is negative, and u of x is 1 if x is positive. And g bar is g of p prime, if you want to know. And it measures the difference between p and p prime. Okay, so you can use these two expressions to characterize the collision operator. And then our method for a broad overview of this method for proving cancellation without the cancellation limit is as follows. So if you take the norm part of the collision operator that I told you about earlier, and you take an inner product of n of f with eta in L2, then you get the integral over dp of zeta of p times eta of p times f of p minus this expression. And then, hold on, let me take one more drink of water. So then you have the integral, so then you minus the integral dp of eta p times dq times integral d omega. Then you have this kernel. Then you have f of p minus f of p prime, and then you have some Maxwellian equilibriums here, the square root of j of q prime. This is just what you would get. And the Maxwellian equilibriums are good. They actually help you. And so the broad overview is to reverse the center of momentum reduction to lift up the 12-fold integral involving the delta function over all of the variables. So you go from dp, dq, and d omega, and you transform that into dp, dp prime, dq, and dq prime. But then you also have a delta function. And then you can reduce the integral to the relativistic Colloquium representation by taking out the p and p prime variables. And so you integrate over dp, dp prime. And dq prime, so you can reduce down to dp to an integral over dp, dp prime, and d pi of q. And so typically we can evaluate the integral dq, d pi q directly, and then we're left with a linear dependence on p and p prime and the remaining integrals of dp and dp prime. And this approach allows us to estimate the cancellation, although there are many, many more details that I'm not telling you about. But this is the, so yeah, so that's the, that's what I want to tell you about the proof. Okay, so thank you. And these are the 3 papers that I told you about during the talk.
So
thank you.
Yeah, thanks Bob for the very good talk. Thank you so much. Okay, so time for questions. So any questions from the audience? You can voice out or either type in the chat room. So any questions from the audience? Yeah, maybe the audience needs some time. So let me ask my question first. So
Okay.
I have 2. So the first one is much more general. So behind the analysis, so what is the physical reason or mechanism so that the crucial change of variable, I mean from P prime to P, is not well defined in the relativistic case?
I don't know. So your question is, what's the physical reason why the change of variable from P prime to P is not well defined in the relativistic case?
Yes.
I wish I had an answer for that. I mean, I could also ask the question, what's the physical reason why the change of variable is well defined in the in the Newtonian case? And you could say, well, because it's very natural. But I could say, well, what does that mean, natural? It feels like it should be true. This feels like something that should be true. But I don't know what that means physically. In the relativistic case, one thing that I can say is that there's a lot more dependence on, there's a lot more interplay between the variables. So the geometry, let me go back to that. I apologize for going through these so fast. So here, this geometry that's sort of mapped here is hyperbolic. So this is kind of mapping a hyperboloid, and so it's asymptotically flat at infinity, and the geometry of in the Newtonian case is analogously parabolic, and it's not asymptotically flat at infinity. But these expressions are much more complicated in the relativistic case, even though, because of the hyperbolic geometry, even though things are asymptotically flat. And there's more than one angle here, so there's only one omega, but there's it shows up in two places. So it shows up just as omega here, and it shows up as P plus Q dot omega here. And so these quantities cannot be written in terms of one theta. So in the these quantities cannot be written as a function of theta. And that's something that's not true, and that's you can do in the Newtonian case. So if I skip ahead, these analogous quantities can be written as a function of cosine theta. So that's a substantial difference.
Mm-hmm. Yeah, so thanks for the answer, even though it's so complicated, so not very clear about the physical reason behind. There is another questions that I have. This is a technical one. So
Yes.
in a classical, I mean in the non-relativistic case, so Boltzmann
Yes.
equation has an angular singularity, so that the analysis is hard. Wow. Are you okay, Bob?
Yes, I apologize.
Yeah, it's okay.
I have a smart light bulbs in my office, and they are programmed to turn off at 11 p.m. because I'm usually asleep before then, and if I'm not, they're telling me to go to sleep, I guess. But I wake up very early. I wake up at 6. But I forgot about them today. I'm sorry.
Yeah, thank you so much for
Sure.
accepting our invitation in the
Sure.
late evening. Yeah,
No
due
problem.
to the different time zone, we don't have other choice. Okay, but let me repeat my questions. So my question is the Boltzmann equation, I mean for the Newtonian case, then has
Yes.
the angular singularity, so that the analysis is hard. So now in the relativistic case, is this angular singularity stronger or weaker? How can we see this in the mathematical analysis?
Oh, it's the same order.
Oh, it's the same order.
So here, okay, you can see that right here. So it's equally strong. So here you have theta is to the order -2 minus nu in the Newtonian case, where nu is between 0 and 2. And here in the special relativistic case, theta is also of the order minus 2 minus minus gamma, where gamma is between 0 and 2. So it's the same order. And it's kind of that's kind of the whole range of possibilities, because when gamma goes to 0, you're sort of approaching you're approaching a 0 order angular singularity. And when gamma goes to 2, you are kind of approaching a whole derivative, or whole 2 derivatives. So depending on how you look at it. So this is this is the whole range of fractional derivatives that you can use. So it has this angular singularity has the same power.
So which means in terms of analysis, the difficulty in this part is the same.
Yes. So the difficulty in terms of the order of the angular singularity is the same.
Okay,
I think that's fair to say. Okay.
Okay, so there is one more question from the chat room,
Yes.
from the Professor Yongyu. So let me read out. Hi, Professor Strang. May I know if the relativistic Maxwellian the only equilibrium solution?
Okay, so yes, so you're asking if the relativistic Maxwellian is the only equilibrium solution to the Boltzmann equation, to the relativistic Boltzmann equation. And the answer is sort of. So the 0 is also an equilibrium solution, but that can be thought of as a special case of the relativistic Maxwellian, but it's qualitatively different because this is a non-zero quantity. And so a lot of the analysis is different. And this is a normalized constant version of the general solution, the relativistic Maxwellian. So there is really a 5-parameter family of relativistic Maxwellians. And so I worked on that a little bit in my work with Jared Speck on the Hilbert expansion, because in that case you express the solution to the relativistic Euler system as the 5 parameters in the relativistic Maxwellian. And I haven't really written them here, but I mean I've written them partially here, but there would be the solution to the Euler system would be in terms of a Lorentz and a product in this exponential. But so if you include that 5-parameter family of solutions, then among sort of a class of regular solutions to the Boltzmann equation, yes, you can prove that those are the only equilibrium solutions.
Okay, so thank you so much. Any more questions from the audience or chat room? Okay, if no, then thank you so much for Bob. So you gave a very inspiring and interesting talk.
Thank you a lot. Thanks a lot for having me.
Yeah,
thanks for the invitation.
Thank you so much. So then that's the end of today's seminar, Colloquium. Thank you for everybody. So thanks for coming.
Thank you. Thanks everyone for coming.
Yes. Okay, so thank you everybody. Okay. Bye bye. So in chat room there are many people fans you Bob.
I see. Thank you everyone.
Okay, so
thanks for coming.
Yeah, but we can talk more later on.
Yeah, sure. Okay, let's talk more later.
Yes. Okay, so let me end the meeting today. So we should have a good live stream.
Thank you.
Bye.
Have a nice day. Bye.
Bye,
Thank
everybody.
you for meeting
yes
slightly early to accommodate me.